The next team is Team 13, CHICO, and one of the speakers you've already heard. Team 13.
Greetings. Hello again. Team, this is Francisco Suarez, Preston Miller, myself, Joshua Mendez, and we will be talking to you about an instrument we've developed over the last couple of years, or not couple of years, couple of months, to address the problem of space weather phenomena affecting both spacecraft, like telecommunication satellites, and also electrical systems on the ground, like power systems. So just a quick geophysical background before we get into it. As you all know, the Earth has a magnetic field, which is caused by the liquid core rotating in the center. There are two types of field lines, closed field lines and open field lines. Closed field lines are field lines that exit one pole and re-enter in the other one. Open field lines are field lines that mix with what's called interplanetary magnetic field lines, which are magnetic field from the sun and other bodies in the solar system. So the closed field lines comprise what are known as the radiation belts. These are locations where charged particles coming from the solar wind become trapped with the field lines and cause a large array of space weather phenomena like the aurora borealis and other effects. So in this diagram, we see a simplified image of how a particle interacts with a magnetic field line. When a particle approaches a field line, it'll start to gyrate around the field line, and the angle its velocity vector makes with the vector of the field line is called the pitch angle. So as the particle moves poleward, as can be seen in the image, the magnetic field increases at this point. So eventually, the parallel component of the velocity vector becomes zero, and the particle will stop. At this point, the particle will move back along the field line to the opposite pole, and will continue to do so if another effect is not included. So what are these other effects? Well, the location where these mirror points occur are a function of pitch angle. So when you have a high pitch angle, the mirror points occur at lower latitudes, and when you have shallow pitch angles, the mirror points occur at higher latitudes. If the pitch angle is low enough, these mirror points will occur somewhere over here and over here, where the atmosphere is, and therefore you'll get collisions with atmospheric neutrals, and the particle will probably be lost to the atmosphere. So these comprise the radiation belts, and the set of angles that will give you, will result in particles being lost to the atmosphere is called the loss cone. So the termini of these radiation belts is what's known as the highlighted trapping boundary, and that's what we're interested in studying. It is a boundary that is very sensitive to space weather phenomena like solar flares. Solar flares cause a lot of damage to space-bound systems, and so there's a lot of money going into researching and trying to understand how we can mitigate these effects. So the sensitivity of the highlighted trapping boundary might seem like a good place to start and try to figure out a model and a preventive model for space weather systems.
All right, so from all this, a couple big questions arise, such as how do space weather phenomena affect the motion of the highlighted boundary and the position of it, and how do scattering mechanisms in the atmosphere modify the pitch angle of particles. So for that, we've developed CHICO, which is an imaging electron spectrometer, and it's designed around a readout electronics for nuclear applications chip, which is able to amplify and shape incoming particle detections. So what it does is, as the satellite crosses the high latitude trapping boundary, the IES will pick up the collisions, and then we'll know exactly where it is and how it's moving as the satellite orbits. So, and it's based on a similar instrument, which is to be flown in the upcoming Air Force DSX mission, and it needs to fit within half a standard CubeSat unit, which is 500 cubic centimeters. So it operates by two 6-pixel silicon detector chips. As shown here, you can see the 6 pixels. The charges hit the pixels, and then it's collected and amplified and shaped by the RENA chip. And from that, these signals are then digitized by a 12-bit analog to digital converter. And from this, it goes to another board which has an FPGA on it, which also controls and configures the RENA, as well as extracts the data and transmits it serially to a single board computer, which is also separate on the satellite, but separate from the instrument. And this just shows a overview of the systems. So the particle collisions will happen on one of these two telescopes, which each has a 6-pixel silicon detector, and the RENA will take the impact, shape it, and then send it to the FPGA when prompted, and then the FPGA transmits it to the single board computer. And it all runs on the same electrical power system, which provides 12 volts and 5 volts DC.
So this is a CAD drawing of the analog portion of the board. This board has the RENA chip, which is seen in the center, our analog to digital converter. The two telescopes are mounted in these locations here. So when an event occurs, a particle will hit one of the pixels on the detectors and will trigger a signal that the RENA will send to the FPGA. The FPGA then proceeds to clock out the address of where this event occurred on the 12 pixels from our detectors, and all the shaping and amplification is done within the RENA. After that, the analog output is passed to a differential output. It's buffered and sent to the ADC for digitizing. Here's a photograph of the completed instrument and the digital, namely the analog portion where we can see the RENA chip, our high voltage power supply, which is used to correctly bias our silicon detector chips, the ADC and the connector that goes to the FPGA board. It's all housed in an aluminum structure to improve noise performance.
As mentioned, the second board included in this instrument, CHICO, is a digital board. The main component of this digital board is an FPGA. This FPGA will provide the control signals and the configuration signals for the RENA chip, as well as it will collect data from it and the ADC, and we'll send it serially to either a computer or a DPU, so it will function during flight. The reason why we have chosen an FPGA is because there's a need of high frequency simultaneous signals, and this is what FPGAs are designed for. Also, we needed several inputs, as we will see in future slides. There are many inputs and outputs required to interface with the RENA, and also the FPGA has a built-in capability for low voltage differential signaling. In such a noisy environment as in space, and especially the radiation belt, keeping signal integrity is necessary, and that's why we have decided to transmit data through LVDS in order to add that extra level of noise immunity. Here's a block diagram of how the FPGA interfaces with the RENA, how it also provides a clock for the analog to digital converter and collects data from it and transmits it serially. Here are the three modules that are part of the code that will be programmed in the FPGA. There are three modules that deal with that interface with the RENA. One is the configuration module. One is the readout module, which is the one in the bottom right. Sorry for the wrong name there. And there's a top module that interface both of these modules. Along with these modules, we have also included a UART transmitter module, several clock dividers to generate the clock for the serial transmission, as well as creating a pulsar to test the RENA chip. Here's the timing diagram of the response of these modules. This is specifically the readout module response to a given stimulus. We can see here in these two clocks are the ones given in order to read out the 36 channels of the RENA chip. We can also see here the 4 clock ticks for the EDC and how we recovered data back in here. So the FPGA that we have chosen to include in this board is a Spartan 3. As said before, it includes LVDS signaling. It also provides us with different configuration methods. We can configure it directly, or we can configure it through a PROM. We can write a program through the PROM in order to, for more convenience, basically. If a power reset happens, or if we just reset the chip, then we can just load directly the program from the memory instead of having to reflash the FPGA. The FPGA also works at a wide clock frequency range, and it has a decent amount of internal memory, but just for safety, we have included that external memory.
So this is the latest version of the digital board that we designed, we laid out. Getting it to configure was a tricky part. So how it is now, you load it with JTAG, which is USB to a computer. It loads to a platform flash PROM, which then needs to load the FPGA on power up. And then it interfaces with Arena through this connector. And we also needed voltage levelers because the logic levels of the FPGA are 3.3, the logic levels of the Arena are 5, so we needed to convert that between them. So this is the second revision of the board, and we corrected a lot of our mistakes, and we were able to program it correctly this time. And this is what it looked like, fitting into the casing. And testing, we need a way to test it on ground. So there are 2 ways. One is use a special pulsar machine, and the other is which is the way we did, to use a scaled pulse directly from the FPGA, which simulates a particle impact. And the result of that from the silicon detectors looks like this. After shaping by the Arena, you get these 6 pulses, 1 for each pixel.
Great. So the final requirement from our customer was that the instrument fit within a volume smaller or equal to 500 squared centimeters. So this is the CAD drawing of the instrument housing itself. What will be given to the people who interface this instrument on 2 upcoming CubeSat missions. One is the Time CubeSat mission, and the other is a CoQSat down in Puerto Rico. It was manufactured by the scientific instrument facilities down in the physics department. This is a photograph showing the completed CHICO instrument compared to the LCI instrument, which is the larger version of this instrument. This instrument contains 3 telescopes, while ours contain 2. However, the performance is similar. And finally, this is what the instrument looks like incorporated into the Time CubeSat, which is a 1.5 unit CubeSat. It's a result of a collaboration between the ECE department, the mechanical department, astronomy department, and the physics department. So with that, we conclude our presentation, and we'd like to take any questions.
You said you had a, what was it, 12-bit pipeline ADC, just one ADC?
Yes, just one ADC.
So I wonder what the maximum rate of particle hits you could handle.
Right, it's 20. It's around 20, 25 megahertz is the rate at which the particle collides. That can be set. So that's the maximum speed of the ADC, and that's what sets the maximum particle hit, and that can be configured in the Arena using the configuration board to send to it. Any other questions? Yeah.
Since you've designed this system to fly in space, what kind of
concerns, well, first of all, our budget, we should mention our budget is much more limited than the LCI mission, so we can't afford to populate the boards with rad hard components. So most of the components, with a few exceptions, are normal components that you can either buy at HQ or Radio Shack. So we're expecting a shorter lifetime in general for an instrument like this, but then again, the cost for this instrument is much smaller than what it was for the LCI mission. Now, one of the bigger concerns we have is how to dissipate heat. In space, there isn't air, so you can't just put a fan on your instrument and expect it to cool down. So heat has to be removed conductively. So our 6-layer board and our 4-layer board have thermal planes, which are essentially large copper cores on one of the layers. And these are thermally sunk to the mount holes for the boards. So heat is dumped into the satellite structure, cooling the boards. And one of the things that will happen this summer is an actual thermal test to see how the boards behave under stresses like this. Yes.
Did you look at heat pipes to get rid of your heat?
Say again?
Did you look at heat pipes to get rid of your heat?
No, we did not. I'm not familiar with that kind of technology. What is that?
It's like a wick inside the copper,
I see.
so it condenses the wet end, and
I see.
it's
No,
faster than a heat sink.
I
Yes.
see. Okay, we might consider it. I mean, depending on how the thermal tests go, we may consider it for an option. Thank you for that suggestion. Yeah.
How does your instrument know where it's looking? Does it have any attitude awareness?
Right. Yeah. So one of the other projects related to this satellite was a physics thesis, which was related to the attitude control system. So we can tell by using 3 methods. One, we can look at the solar input on solar cells, so we can know where that is. We also have a magnetometer, so we can measure where we are assuming the Earth is magnetic field is a dipole. We can figure out where we are. So those are the main methods. Because this instrument is fairly power hungry. It takes about 3 watts. So we have to duty cycle. It can't be on all the time. So we need to tell it when to turn on, and specifically over these locations. Highlighted charging boundary 60, plus and minus 60 degrees of latitude. So that'll tell the instrument when to turn on. Yeah.
Did you have any special consideration about how you mount the boards within the housing?
Considerations. The main considerations were for the boards not to act as drum skins during launch where you have vibration. If you mount them directly just on the sides, there's nothing to support the center, and during vibrations it might crack a board. So that's one of the reasons we put the connector in the center region of the board to provide an extra support in that region.